Hi, this is my video number 23. It's not focused. Number 23. It's not clear, yeah? Alright. Okay, so I'll talk on the multiple integral. Multiple integral. Okay, so first we let a function be defined on region R. Let a function f of xy be defined on the region R. Region R. How to make it more focused? Alright, on the region R, where R is given as so the region R where this R is given as a x b and y C and D. Okay, so in terms of I can figure this like so we have, so this is x from A to B and y from C to D. So this is our region R. So this is our region R inside there. So this is our region R. Okay, so what we're going to do is we split this region into small pieces, right? So I can have like split this on x direction, as well as I can do the same for the y direction. Okay, so if I pick one of these, we take it out this. Okay, so let's say this is the in the x direction. Let's say delta x, and in y direction let's say this is delta y with some other. So let's say this is I, this is j. Okay, for each of these point we have x0, x1 and so on up to xn. So for y as well we have y0 until let's say ym. Okay, so for x0, x1, x2 up to xn, and y from y0, y1, y2 and so on up to yn. So basically our delta x, our delta I would say, our delta xi, this is xi minus xi minus 1. So we have that distance here. Okay, so that distance, this is delta x. So the same thing with delta y, j is yj minus yj minus 1. So if you multiply this, delta x, delta y, so this is we take out one box. So let's say this is delta x I here, this is delta y j, that okay, that line. So what we can do, we can find the area of that small region, I would say, area of let's say this is Ri. Yes, the region of Ri is given as delta xi times delta y yj. So in order to find, so we able to find one area, small area there. Okay, in order to find whole area of that region, so what we do is we add up for all x's and add up for all y-axis, so and multiply both things. So therefore, based on this thing, all right, so therefore the area of R is we just sum up for I1 to n, we sum up for j from 1 to m. So delta x I, delta y, delta yj. So that will give us the area of that region. Okay, so that's for 2 dimension, or for the on xy plane. So if it's involve z axis, so let's consider in 3D cases, in 3D case, where so we let our f is given as a function of xy, function of xy, be defined on R, defined on R. Yeah. So where R is given as A, B, and C to D, or Y, C to D, and we have Z, which is less than those function x and y. So if you can figure out, we can consider this as a surface, yeah. So the region bounded by some surface. So if I can plot this a little, or sketch this, so we have let's say this is our z. Okay, z is given as fxy, and those bounded on xy plane. So let's say x from A to B, you can see those things, x from A to B, this is x, y, and we have z here, and y from C to D, this is C, this is D. Okay, so on xy plane, again I can do this, split into small pieces, right? We can split interval AB into sub-interval, CD into sub-interval. So I can do this as much as I want, and I can do only Y as well. Okay, so if you consider one of this point here, one of these boxes, okay, at this some particular points, let's say I take the midpoint there. So let's say this is our xk there, the case points, and let's say this is our y, some other, let's say yk there. Then of course, if I evaluate this xk yk, I can find the height of this. Yeah, that's called f. I think we use a different notation, k and ijk yl, say. Okay, so I can have f kl, which is we evaluate at point sk y yl. So what we can do, we can have the height of those surface from the xy plane. So if we multiply for this, where delta x, for this, let's say those delta I, multiply with that delta j, yj, so this will give the area as above, as we have here. Okay? That will give you the area, and then we multiply with the height of those surface. So f at x I yj, I would say. Okay, so here I use k, so this is I j. Okay, I think this one also I use I and j. Okay, so I can have those things, and then to find, so what we have here, this is the volume, one of those value. Okay, so to find the volume for the whole region bounded by this xy, bounded by all those things, okay, inside there, bounded by those things. So to find the volume, we need to sum up each of those things. All right, so we have f xi yj, and we have delta x I delta y delta yj. Okay, now this is I from x naught to n, or you can make I equal to 1, is still okay. J equal 0 to n, so that we can have x naught, y naught, and so on and so forth. And then if we take n in m goes to infinity and m goes to infinity, so what we have basically, those summation, we got the volume, we got those summation, we have double integral over the region R, and we have our f xy, and we have dx dy. So it means from there we can see that the integration or double integral over the for a function f, yeah, with over the region R will give you the volume. Yeah, we take a limit of those things. All right, so let's see a couple of terms that we might need to use later on. First, we look at the Fubini's theorem. Fubini's theorem. I think it's theorem. It's a Fubini 1. Okay, so let f xy be defined on R. Defined on R, where R is the region given by x between A and B, and y between C and D. Okay, then so if you look at the region here, this is x between two constant A and B, and y between two constant C and D. So basically our region just look like a square for x from A to B, y from C to D. So this is our region R. That's our R. Then the integral over region R of fxy dr, this is, we integrate x from A to B, y from C to D, f xy dy dx. Or you can use either y first or x, then x, or x first then y. You can use that, provided that f must be a continuous function. Yeah. So be I think be defined, be continuous and defined on those region. Okay, now we look at another theorem. You call it as Fubini's 2. Let a function f xy be continuous on R, where R is given as the region R is given by x between A and B, and y between G1 x and G2 x, where G1 G2 are continuous, where G1 x and G2x are continuous on interval AB, then we integrate R fxy dA. This is given as, we integrate, so let me sketch the region for R in this case here. That's our R, okay. For x between A and B, so let's say that, and y bounded by two functions. So you may consider, let's say, function y look like, let's say you have something like this or something like this. This is G1, y equal to G1 of x. This is y equal to G2 of x. So our region R is not rectangular anymore, but in this case a more general region. This is our R. So bounded by curve G1x and G2x and a straight line x equal to A and B. So then in this case the integral or the evaluation of the integral is given as, we integrate x from A to B, y from G1x to G2x, f xy dy dx. Okay, so please note that when we do the integration or double integration or multi-integral, remember that the most or the outer integral here must be from integer to integer. You cannot put it this way. So this is different than G1x or y. I can say y G1x to G2x f xy and integrate x from A to B dx dy. No, this is not working correctly, because later on you won't get any you will got in a variable, your answer in a variable. So but whereas in this case we want it as we want it the exact solution. So means the most outer integral must be from integer to integer, not variable to variable. So please note this. Let me give you an example. Before that, let me give you another theorem. Let's say Fubini's theorem 3. Fubini's 3. So let f be continuous on R on R, where our R is given as Y between C and D, and X between let's say H1X to H2X, where H1X equal to H1X, this is H1Y, should be a function of Y, should be H1Y, and X equal to H2Y are continuous on interval Y between C and D. Then the integral over R f xy dA. Okay, so let me figure out the region for this. We sketch a little bit. So we have y from C to D. Okay, y from C to D. So we have y from C to D, and our x between two functions h1y and h2y. So I can have, let's say, h1y, let's say x equal to h1y is something like this. This is x equal to h1y, and another one is x equal to h2y. So this is our region. This is our R. So the integral becomes this is y from C to D. Remember that, as I mentioned earlier, the most outermost integral must be from, the limit of those must be from integer to integer. So in this case, we integrate x first, h1y, h2y, f xy, dy, dx, dy. Okay, so let's see some example. And I only have one example here for the rectangular case. Yeah, find the volume. Find the volume of cuboid enclosed by z equal to 4 minus x minus y, and R is given as 0, x 2, and y 0 to 1. So if we sketch the region, the region here R, so what we have, x from 0 to 2, y from 0 to 1 here. So this is our region. That. Okay, and we have surface z is given by this. So this you can consider our function x y, yeah, fxy. So to find the value, we just integrate. Yeah, what we need to do is to integrate over R f xy dA. So this is, we integrate our R x from 0 to 2, y from 0 to 1, and our function is given here, fxy. So our fxy is 4 minus x minus y. We integrate with respect to y, then integrate again with respect to x. So you can do this. I just give you the solution 5. Yeah, and then we may consider another example where R, so let's say this is 1, let's say this is 2. If I have R is given as x from 0 to 2, say 0 to 2, and y, let's say some function, I want it x 0 to 2, 0 to 2, and then I want, let's say, function look like that and like that. Okay, so let's say this is y equal to half x, and then to 3x, y 3x. Okay, you can try to evaluate this thing. So evaluate this, we have R, so this is our region, this is our region R. Okay, so we integrate over the region R of f xy dA, then integrate x from 0 to, so x from 0 to 2, and our y from half of x to 3x, then our function 4 minus x minus y dy dx. Again, you can evaluate this. You got whatever. I don't have a solution for this. I just come up in my mind just to give you the example or the idea what is Fubini's theorem 1, 2 and 3 look like. So this is, we have for the theorem Fubini's number 1, this is for Fubini's number 2, and if you want for Fubini's number 4, you can change. Yeah, I can have let's say Fubini's number 3. Let's say I give you an example for this. We use the same function. Our z or fxy is given as 4 minus x minus y, but our r is given, let's say, y from 0 to 1 and x from 2 functions. So let's say we have this y from 0 to 1, this is 1, so that's our y, and then let's say we have a function that and that. Okay, this is x is equal to 1 over 3y. Let's say this is function x equal to 3y. Okay, so this is h1 y, this is h2 y. So our region now is here. This is our region. This is our R. Okay, so to evaluate this integral, because we have the constant to constant, means for y exists, so we integrate x first, then y. So integrate R fxy dA. Okay, this is equal to, we integrate first y, second y, the outer integral from 0 to 1, and then we integrate the inner integral is x from h1, which is 1 over 3y to 3y. Our f is 4 minus x minus y, now dx dy. Again, you can come up, you can solve that yourself. Okay, so those 3 examples on the Fubini's theorem 1, 2 and 3. Now what we have seen is that we can integrate, or we can evaluate or the integration around a region R. And before that, we can evaluate the integral over the line, or I can say line integral and region integral. Now we go to the theorem that relate these two situations, the line integral and the closed region. Yeah, line integral and the closed region, or we can say closed contour. So that's we call it as a Green theorem. Okay, so this Green theorem give the relationship between line integral around a simple closed curve. A simple closed curve C and a double integral over the plane region D bounded by C. Okay, so before I state the theorem specifically, so let me describe what is C, what is D. Can just a minute. I have a little bit. Okay. I have some disruption actually. So let's look at this the relationship. So before we go to the theorem itself, let me discuss, or let me describe what is C, what is the region, what is the region D. Okay. So we have basically in XY plane. Okay. So we have those C. Let's say this is the contour or closed curve C, that's our C, and the region is enclosed by C. So this is the region D. So this is our D. Okay. So we have a closed contour or closed curve C, and D is a region bounded by C. So with that, let me prove the theorem. Let me write the theorem first. So let's say be a smooth, piecewise smooth, simple closed curve. Let's see be a piecewise smooth simple closed curve and positively oriented, yeah? and positively oriented. In the plane and let D be the region bounded C, be the region bounded by C, so if P and Q if P and Q have a continuous partial derivative, have a continuous partial derivative on an open region, on a region D, then on the region D, then the integrate over the contour C closed curve, closed curve, positive oriented, P dx plus Q dy, this is equal to integrate over region D del Q del x minus del P del y dA. So in this case, our P is a function of x and y, and Q is also function of x and y. So you need to memorize this one. This is the what we call as a Green theorem, the relationship between the line integral and the integral bounded by C, the region bounded by C. So let me give you a proof of this theorem. We're going to prove this theorem. Proof of Green theorem. So let's see be a simple close. Let's see be a simple close, piecewise smooth and positive oriented curve, positive oriented curve on the plane, and we have PQ del P del x or del Q del x del P del y, all these are continuous. All right. So those curve C, so what we have is that we have x and y, and we have, let's say, those are piecewise smooth curve. We have this is let's say this is equal to C, y equal to f1x, right? Let's call this C1, and this is for C2 positively oriented, so we have that, and we have C2, let's say y equal to f2x, f2x, and this is the region bounded by C. That region is D. So if you look at the Green theorem here, so let me write this. What we have is that integrate, I want to write this here. If we integrate over the region C, P dx plus Q dy, this is equal to integrate over D del Q del x minus del P del y dA. Okay, that's what I want to show. If I can show So if we can show, that if you look at this p dx equal to negative of those and q dy equal to that, then we're done. Yeah. If we can show that integral over c p dx equal to minus double integral over d del p del y dA, and we integrate over c q dy, you take the other one, q dy, this is equal to integrate over d del q del x dA. Let's say this is number 1, let's say this is number 2. First we look at the number 1. Now from the given region there, we know that our C, so let's say this is from A to B, yeah. Our C consists of C1 and C2, where our C1 is given as y equal to f1x and x between A and B. So you can see our C1 given by y f1x and bounded by A and B, yeah, the interval AB. And C2 is given as y equal to f2x and the interval, or in the interval x between A to B as well. So our region D, so from there our region D is given as all point xy, yeah, region D is inside there, okay. So point xy, where x between A and B and y between G1, this is, I use F, so just a minute, so I change this, I change it to G, I change this to G, so our y, this is G, this is G, you know, just to align with my notes. G1x, G2x. Okay, that's our region D, where G1, G2 are continuous function. Now, remember this option, we have equation 1 and equation 2. We're going to prove that one by one. I'm going to prove just one, and number 2 you do it by yourself. Okay, so now consider the right hand side of 1. We consider right hand side of 1. What we have is that we integrate over region D del P del Y dA. Yeah, this is the same as we integrate A to B. We integrate, this is for Y and X from G1X. Let me say again. Sorry, this is X from A to B and Y from G1X to G2X. Okay, del P, we have del P, a function of X and Y with respect to, we integrate respect to those things dy, del P del Y, integrate respect to dy and dx. So we can solve this. Integrate, differentiate, we got that function again. Okay, so what we have, this is integrate from x A to B, and this we have P of x, our y is G2x minus P of x G1x dx. Then So let's see this again. This is right side of 1. Now we look at the left hand side of 1, which means I want to look at this left hand side of 1. Okay, so left hand side of 1, where our C is given by C1 and C2. So now if we integrate C of P dx, this means that we integrate over C1 P dx plus we integrate C P dx. Okay, so for C1, so we integrate C1 P dx. Our P is xy dx. So this is the same as we integrate x from a to b. P, our x, y is a g1x, because our C1 is given by y equal to g1x dx. Whereas for C2, this is for C2, P dx, this is we integrate from b to a, P x g2x dx. This is just the same as minus integrate a to b, P x g2x dx. So therefore, we integrate over C P dx. That gives us, we integrate C1 here. C1 is given that. So a to b, P x g1x dx plus minus integrate a to b, P x g2x dx. Okay, so if you compare right hand side and left hand side, compare left hand side and right hand side, what we have shown here. This is from right hand side, we got this, and from left hand side we got this. So you can see they are just same. Here you can combine these two. Okay, so what we have is that we integrate over C P dx. This is the same as negative of integrate over d del P del Y dA. Okay, and then you need to evaluate the 2, or to show 2. Show the equation number 2. For equation number 2, you just follow the same step there, except you need to change the function. Then I want you to do this. Now adding up the first and the second, you get the solution of the green theorem. So you add up those things, P dx plus Q dy, that will give you integrate the del Q del x minus del P del y d of a. So this is the green theorem. Alright, I have an example for this, but I don't think I can give the example right now. So I stop here, then I'll give an example in the next video. Alright, so that's all for now. Thank you.